Welcome to the Deep Dive, where we break down complex technical blueprints to give you the strategic insights you need. Today, we were going deep, really deep, into heavy commercial vehicle engineering. We're looking at the N3 class cement mixer truck. You know, the one, that huge 24, maybe 32-ton behemoth you see all over our cities. And if you stop and think about that vehicle, its whole job is a massive paradox, really. The traditional diesel mixer is powerful, it's dirty, and it is incredibly noisy. But these things have to work in cities, in environments that are getting less and less tolerant of all that noise and all those emissions, and often at very sensitive times, like a late-night construction pour. The core of the problem, the real contradiction, is what engineers call the PTO problem, the power takeoff. See, a normal mixer has to keep its giant diesel engine idling all the time, just to power the pump that spins the drum. It's an incredible waste of fuel, it creates pollution, and that noise basically puts up a wall to city access. It's a powerful truck that's, held back by its own design.
And that specific constraint, that problem, is the exact trigger for this deep dive. We're not just looking at a concept today. We are analyzing a core strategic document. It's called a Function Specification Definition Statement, or FSDS. This document was generated to guide a major engineering team, and it's their roadmap for developing a P2 hybrid system on a 400-volt platform, all combined with a dedicated electric power takeoff, the ePTO, for this exact N3 class mixer. Our focus here is on that decomposition process. How do you make sure the final product hits that perfect balance of performance, aggressive fuel economy, and this is critical, ironclad functional safety under standards like ISO 26262. So this isn't some technical wish list. It's a blueprint. It's data-driven, based on really intense analysis of how these trucks actually work.
Okay, right. Let's unpack this. So our mission here is to dissect the engineering DNA of a product that's designed to maximize regulatory dividends, while at the same time giving huge cost of ownership relief to the people who actually run these fleets. So this FSDS, it's basically defining a product that flips the script. It takes the mixer's biggest weaknesses, those cost and noise headaches, and turns them into its biggest strengths. We are breaking down the entire engineering blueprint, from the regulations all the way down to safety and thermal management.
To really get the solution, you first have to understand the pressure. The global pressure is just relentless. The sources we're looking at describe it as a legislative pincer movement. For a long time, these vocational and construction vehicles, they sort of got a pass. They had exemptions.
But these are over.
Completely over. Governments are closing those loopholes, and it's forcing electrification. Just making the diesel engine a little bit better isn't going to cut it anymore.
And this pincer movement, it sounds like it has three pretty distinct blades. Let's start in Europe with this simulation tool, ePTO. For anyone listening who isn't familiar, ePTO is a lot more than just a simple emissions check, right? It's a whole operational model.
Oh, absolutely. ePTO, the Vehicle Energy Consumption Calculation Tool, is the master key in Europe. It calculates CO2 in grams per ton kilometer. And for cement mixer, it uses a very specific construction mission profile. And here's why that's so powerful. The simulation is designed to specifically identify and amplify the negative impact of high-power takeoff fuel consumption.
So it zeroes in on that idling problem we mentioned.
Exactly. When that big diesel engine is sitting at a site, idling for maybe 20, 30 minutes, ePTO sees that all that fuel being burned created zero movement, 0 ton kilometers. But it created a lot of emissions. So the simulation assigns a huge inefficiency penalty to that high PTO consumption. It just blows up the vehicle's CO2 score.
So it's punishing the one behavior that a traditional mixer can't avoid.
Precisely. And the stakes here are just monumental. The EU mandate is that new fleets have to cut their average CO2 emissions by 45%.
45 by 2030.
By 2030 against a 2019 baseline. And look, modern diesel engines are already incredible. They're pushing 46, maybe 50% thermal efficiency. You just can't find another 45% of savings in the engine itself. The hybrid strategy, by killing that high PTO idle consumption, provides the structural change you need to even have a chance at meeting that target. It's become a necessity.
Okay, let's jump over to Asia. China's approach is a bit different, focused on changing the test cycles themselves.
Right. That brings us to China's Phase 4 fuel limits, GB 30510 2024. The limits are getting much stricter, about 12 to 16% tighter than before, but the real engineering trigger, the big shift, is moving to the China Heavy Commercial Vehicle Test Cycle, or CHTC. Specifically, the CHTCD for distribution, which is all about heavy, congested city driving.
So what is it about that CHTC cycle that actually benefits a hybrid?
It's all about the stop and go. The CHTC has much lower average speeds and a way higher frequency of decelerations and complete stops compared to the old highway cycles. For a traditional diesel, that's just a nightmare for efficiency.
But for hybrid,
For the hybrid, every one of those stops, every time you coast to a red light, that's a new opportunity to harvest energy. It maximizes regenerative braking, it's constantly restocking the battery. So the test cycle itself, because it mirrors city traffic, is functionally rewarding the hybrid for what it does best.
and then in the U.S., the EPA seems to have structured their rules almost perfectly to encourage this exact kind of solution.
They really have. The EPA's GHG Phase 3 focuses on CO2 grams per ton mile. But unlike a pure penalty system, it offers very clear incentives. There are specific allowances for hybrid credit and, crucially, idle reduction credit. A cement truck is the perfect candidate to max out these credits. I mean, their whole job involves massive amounts of idle and wait time, like we said, 20 to 40% of their day. By getting rid of that idle, by powering the drum with the battery, the manufacturer can claim these huge quantifiable credits. And they can use those to balance the emissions books across their entire vehicle fleet. The hybrid mixer becomes a compliance tool.
So you got this regulatory stick forcing the change, but the FSDS makes it very clear that the carrot, the real commercial driver, is noise.
Noise is the commercial barrier. Think about it. A traditional diesel idling at a site is putting out 85, maybe 90 decibels. When the pump really ramps up to discharge the concrete, that can spike over 100 decibels. That sound level immediately gets you kicked out of sensitive residential areas. It means you can't do those really profitable nighttime pours.
And the hybrid solution, with its electric drum drive, just erases that problem.
It completely erases it. The FSDS defines the silent operation mode as the core unique selling proposition. The mandate is to achieve a noise level under 72 decibels at a distance of 7.5 meters. And that 72 dBA figure, that's the magic number. That's what satisfies the very strict European PI standard.
So help us picture that. What does 72 decibels actually sound like in the real world?
It's roughly the sound of heavy traffic from about 100 feet away, or maybe a really loud vacuum cleaner. To get down to that level while you're churning 10 cubic meters of sloshing concrete in a giant steel drum, a drum that needs, 8 to 15 kilowatts of power just to turn. It's a huge engineering challenge. But the payoff is extraordinary. See, meeting Pike isn't just about being quiet. It's about what being quiet buys you. It grants what the document calls a 24-hour operational window. A fleet operator with Pike-compliant trucks can bid on jobs that require round-the-clock access. They can get into those expanding zero-emission zones. They can effectively lock their louder, diesel-only competitors out of the market. This ability to monetize hours that the competition can't touch, that's a monumental commercial advantage. It turns noise compliance into a profit engine.
It's fascinating. The FSDS elevates noise from just an environmental metric to a core strategic driver, maybe even bigger than the CO2 reduction itself. It's a shift from just cutting costs to actually expanding your market.
That is the entire strategic foundation. The old mixer wastes time and money waiting. This new architecture is designed from the ground up to capture and monetize that previously wasted time.
This is where it gets really interesting, where you can see the deep analytical work in the FSDS. You can't design this kind of system with just generic trucking data. A mixer isn't just a truck, it's a specialized mobile factory. So the FSDS meticulously breaks down the energy needs across 5 critical phases of a delivery cycle. And if you get even one of these phases wrong, the whole system is sized incorrectly.
This duty cycle analysis is the absolute core. It dictates everything: battery size, motor power, engine choice. Let's start with phase 1, loading or batching at the plant. To mix the materials correctly, you need high-speed rotation. We're talking 12 to 14 RPM. This is a really high load phase. The power demand is a continuous 20 to 30 kilowatts, but it can spike up to 40, even 60 kilowatts as you're loading in all that material.
So how does the hybrid system handle that huge power demand efficiently while the truck is just sitting still?
Well, since the truck isn't moving, the system puts the engine, which is now smaller, into what's called generator mode. It runs at its most efficient point, its sweet spot, and its only job is to drive the P2 electric motor to generate power. That power does 2 things at once. It charges the battery, and it directly powers the ePTO to spin the drum. The goal is to batch the concrete efficiently, sure, but also to make sure that truck leaves the plant with a really high state of charge, maybe 80 or 90%, ready for the work ahead.
Okay, phase 2 is transport. Now we've got a fully laden 32-ton vehicle on the road, and it has to keep the drum turning slowly.
Correct. During transit, you only need slow agitation, maybe 1 to 3 RPM. That's a parasitic load of 10 to 15 kilowatts, just to stop the concrete from separating. But on the driving side, the main challenge is acceleration.
And that's where the P2 motor really earns its keep.
Exactly. The P2 motor provides what we call torque assist, or peak shaving. So during high load events, like pulling away from a stoplight, it picks in. This lets the smaller diesel engine stay in its efficient cruising zone. Instead of the engine having to struggle and burn a ton of fuel to handle that acceleration spike, the P2 motor delivers that instant torque.
You also mentioned something really interesting about the concrete itself, that it's a non-Newtonian Bingham fluid. What does that mean for the drum drive?
Right, so concrete isn't like water. As a Bingham fluid, it has what's called a yield stress. It won't flow until you apply a certain amount of force. In simple terms, it needs a constant, stable torque to keep it turning evenly. In the old hydraulic systems, the drum speed would fluctuate all over the place as the engine RPMs went up and down. That instability is bad for the concrete. It can ruin its integrity, what's called its slump. But by moving to a dedicated electric drum drive, you get incredibly stable RPM. The FSDS actually mandates a speed error tolerance of plus or minus 2%. That stability is a huge, often overlooked quality improvement.
All right, now we get to phase 3. Waiting at the site. This is the financial black hole for the traditional mixer. It can be 20, even 40% of their entire day.
This is the absolute core pain point that the hybrid system is designed to eliminate. The traditional failure here is just catastrophic for efficiency. That massive diesel engine has to keep idling, running at a low, inefficient temperature just to keep the hydraulic pump turning the drum. This wastes 4 to 6 liters of fuel every single hour.
And beyond the fuel waste, there's a long-term mechanical cost to that idling, right? You mentioned wet stacking.
Wet stacking is a really severe problem for diesel engines that idle for long periods under low load. The engine runs too cool to completely burn the fuel, so you get this unburnt fuel and carbon that builds up on the cylinder walls and in the exhaust. This gunk, this wet stack, fouls your injectors, glazes the cylinders. It just leads to long-term engine damage and way higher maintenance costs.
So the hybrid solution is a total negation of this.
It's a complete negation. The mandate in the FSDS is simple. ICEO off, engine off. The high-voltage battery takes over completely and powers the ePTO directly. This one change delivers a 60 to 80% fuel saving just in this one phase. It's the single biggest opportunity for cost reduction, and it gets rid of that engine damage problem.
The FSDS says the battery shifts from being a range device to a work energy reservoir.
Oh.
So let's break down how they got to that number, that minimum of 20 kilowatts of usable energy.
The sizing is all based on the demand profile for static work. You need enough energy to cover a long wait and a full unload. So first, the agitation. The analysis shows that continuous agitation takes about 8 kilowatts. If your mission profile says the average max wait time is, say, 90 minutes or 1.5 hours.
Okay, so 8 kilowatts times 1.5 hours is 12 kilowatt hours.
Exactly. Then you need to account for the unloading itself. One full unload cycle is pretty intensive. It takes about 5 kilowatt hours of energy. So you add those together, you add a buffer for maybe multiple site waits, plus a 20% safety margin for battery aging and delays, and you land right at that minimum usable capacity of 20 kilowatters. That's why the FSDS specifies a total battery pack of 60 to 70 kilowatters. You can use that 20 kilowatt work portion while keeping the battery in a healthy state of charge, which is great for its lifespan.
On to phase 4, unloading. This is where you have to actively force the concrete out.
Right. This needs high speed, variable rotation in reverse, again up to 14 RPM. And initially, the motor has to deliver a huge amount of torque, 30 to 50 kilowatts worth, just to break the static friction. And by keeping the engine off, this entire intense operation is done purely electrically. So you maintain that peak quiet compliance, zero noise, zero emissions. And the electric motor gives you incredibly precise speed control, which is critical for complex jobs.
And finally, phase 5, the empty return. This is when the battery gets paid back.
This is the crucial step that closes the energy loop. The truck is now much lighter, maybe down to 13 or 15 tons from 32. So the system has to switch into an aggressive regeneration strategy. It has to maximize energy recovery from every single braking event, every downhill slope. The analysis shows a huge potential here. 15 to 20 kilowatts of energy can be recovered per day in a dense urban cycle. And that recovery is key to minimizing how much you have to plug in and charge overnight.
So if I'm understanding this deconstruction, the core goal isn't just general efficiency. It's about getting to 100% efficiency in that idle work phase by completely decoupling the powertrain from the work tool.
That is the ultimate strategic principle from this analysis. The design mandates that you abandon the old PTO linkage and move the drum power entirely to its own independent high-voltage electrical system. That decoupling is the single choice that solves the idle waste, the noise, and the concrete quality issues all at once.
So now the FSDS takes all these operational needs and turns them into hard targets. The Vehicle Technical Specifications, or VTS, this is the engineering scorecard. Let's start with dynamics.
Right. The hybrid has to perform better than the diesel it replaces. In a city, acceleration is everything. A traditional mixer is, well, it's a slug. It can take 25 seconds or more to get to 50 kilometers per hour.
That delay costs money and it holds up traffic. What's the new mandate?
Thanks to that instant torque from the P2 motor, the FSDS mandates that full load acceleration from 0 to 50 kilometer must be 18 seconds or less.
Wow, a 7-second reduction. That's huge.
It's massive for safety and just getting around in traffic. And then for the construction site itself, max gradability, which is critical for muddy ramps, has to be at least 30%, even when fully loaded.
Okay, on the economy side, the targets aren't just about meeting regulations. They're about guaranteeing a return on investment.
It's a two-tiered target. The overall fuel saving across a whole cycle is set at 20% or more. That's what justifies the higher price of the hybrid. But the real value, the thing that pays for the whole project, is the site-specific target. The fuel saving during that waiting and unloading phase has to be 40% or more.
And what about guaranteeing access to those special zones?
For that, the pure electric range, or AER, is set at over 20 kilometers. Now, you might only need 5 kilometers to move around a site quietly, but that 20-kilometer number is strategic. It future-proofs the truck, ensuring it can get into those expanding zero-emission zones in cities like London or Paris for years to come.
This brings us to a huge decision in the FSDS, the engine downsizing strategy. Moving from a big 13-liter diesel down to a 9 or 11-liter, that feels wrong for such a heavy truck. Don't you lose power?
You would if not for the P2 motor's ability to provide that torque fill. The P2 motor, specified at 120 kilowatts peak, delivers around 800 newton meters of torque. It completely covers the low-end power deficit of the smaller engine. So when you start from a stop, the electric motor gives that instant kick, and the smaller 9-liter engine feels just as powerful as the big 13-liter it replaced.
Let's talk about the efficiency gain there. Why is a smaller engine more economical even when you're just cruising?
It comes down to something called brake-specific fuel consumption, or BSFC. You can think of it as an engine's efficiency map. A huge 13-liter engine, when it's just cruising under a moderate load, is operating way outside of its most efficient zone, its sweet spot. By downsizing to a 9-liter and using the electric motor for the peak power events, you force that smaller engine to work harder, closer to its high-load, high-efficiency sweet spot during normal driving. That significantly improves cruising economy. Plus, the smaller engine is lighter and cheaper.
Okay, key decision 2 is a big one, maybe even controversial. The FSDS defends using a 400-volt platform when the whole industry seems to be rushing towards 800 volts. Why stick with 400?
This is a classic engineering trade-off. It's about prioritizing reliability and cost over a marginal performance gain that this specific truck doesn't even need. Sure, 800 volts gives you faster charging and lighter cables, but a hybrid mixer doesn't need 350 kilowatt ultra-fast charging. It gets most of its energy back from braking and then charges slowly overnight.
So what are the main reasons the FSDS gives for sticking with 400 volts?
There are two big ones. First is cost and supply chain maturity. The 400-volt component ecosystem, we're talking inverters, pumps, converters, it's just incredibly mature for commercial vehicles. The FSDS estimates 400-volt parts cost only 60 to 70% of their 800-volt equivalents. For a vocational truck, where upfront cost is a huge deal for fleet buyers, that saving is non-negotiable. The second reason is durability and robustness. And for a cement mixer, this is the killer argument. 800-volt systems require extreme levels of insulation to prevent arsing. A cement mixer lives in a world of constant vibration, high-pressure water blasting, and cement dust. And wet cement slurry is conductive.
So you're saying in this specific, really harsh environment, 400 volts is actually safer and more reliable?
Precisely. Lower voltage is inherently more forgiving. It requires less insulation and has a lower potential to arc when that insulation inevitably gets worn down by moisture and abrasive dust. The FSDS prioritizes long-term robustness over the speed advantages of 800 volts. This system has to survive a decade of abuse, and 400 volts gives you that critical safety margin.
Okay, so now we get into the physical architecture that makes all this happen.
Yeah.
First choice is topology. P2 versus P4. I know P4, the electric axle, is tempting for its torque and regen capabilities.
It is. P4 offers fantastic traction, which would be great for muddy construction sites, and it's the best for regeneration. But for a cement mixer, the downsides just made it a non-starter for this first phase of development.
What were the big risks with P4 here?
It would require a massive redesign of the whole truck chassis. The integration is really complex, and crucially, the giant cement drum and its gearbox take up all the space right where you'd need to put the P4 axle and its electronics. The cost and the time-to-market trade-offs were just too big.
So the FSDS locks in the P2 plus ePTO as the way to go.
Yes. The P2 coaxial parallel system, plus the dedicated ePTO, is designated as the optimal choice. P2 is a mature technology. You integrate the electric motor between the engine and the existing automated transmission. And that's key because it lets the transmission gears multiply the motor's torque, which gives you amazing starting power without needing a gigantic motor. It uses the existing chassis space, and it really speeds up development.
Let's come back to that core innovation. The complete decoupling of the drive system and the work system, getting rid of the old hydraulic PTO.
This is the truly revolutionary part. The old system was this inefficient hydraulic loop. The new system uses the dedicated 400-volt system to power the electric drum drive, or EDD. This completely separate electrical path means the drum's RPM is controlled with absolute precision by its inverter, totally independent of what the diesel engine is doing.
So let's talk about sizing that EDD motor. How much power does it need, and how do you get the massive torque required?
The FSDS specifies a permanent magnet synchronous motor, a PMSM, for its high torque density. It's sized for 60 kilowatts peak power, 30 continuous, and it delivers about 550 newton meters of torque at its shaft.
Okay, 550 newton meters is a lot, but to turn a full drum of concrete, you need tens of thousands.
Yeah.
How do they bridge that gap?
That's where the high-ratio planetary gearbox comes in. The electric motor is coupled to a specialized reduction gearbox with an incredibly high ratio of about 140 to 1. That 140 to 1 ratio is the mechanical secret sauce. It multiplies that 550 newton meters from the motor, allowing the system to deliver the absolutely staggering output torque you need at the drum. We're talking 60,000, maybe 70,000 newton meters to break the static friction of settled concrete. And this whole electrical mechanical chain is way more efficient too, over 90% compared to maybe 60 or 70 for the old hydraulic system.
The FSDS is really clear that this whole engine-off capability depends on electrifying the other essential vehicle systems. Why is that non-negotiable?
It's an absolute necessity for functional safety. When you shut the engine off at the site, the things it normally drives also stop. So if your steering pump is still mechanical, the driver suddenly loses power steering. You can't maneuver a 32-ton truck on a crowded site without it. And even more critically, if the air compressor stops, the vehicle starts to lose air pressure for the brakes. Losing brake pressure is a severe, severe safety risk. So the 400-volt system also has to power an electric steering pump and an electric air compressor. That ensures you have full braking and steering even in silent engine-off mode.
Finally, we have to talk about the limp home plan, the mechanical redundancy for that worst-case scenario that engineers call canning.
Canning, or is the most financially damaging failure you can have. If the entire high-voltage system dies, a major inverter fault, whatever, and the drum stops turning, the concrete starts to set. In a few hours, you just have a giant, solid block of concrete inside your drum. The truck is useless, you might have to cut the drum off, and the whole load is lost. The financial hit is immense.
So the blueprint has to include a manual override, something totally independent of the electronics.
Yes, mechanical redundancy is a mandated failsafe. The architecture requires a standard ISO emergency interface on that electric planetary gearbox. If there's a catastrophic failure, a technician can come out with a rescue truck and connect what's called a soft shaft to its PTO. This external power source can then manually rotate the drum, allowing the concrete to be discharged before it solidifies, saving the vehicle. Now we have to shift from performance to the absolute foundation: functional safety under ISO 26262 and durability. When you introduce complex 400-volt torque control into a 32-ton machine, the safety risks go to the highest possible level.
The hazard analysis, the HARA, and the FSDS flags two major, really severe hazards. Let's start with a driving one: loss of regeneration.
Right. Hazard example 1 looks at what happens on a long, steep downhill drive. The driver is expecting the electric motor to provide a lot of braking force through regen, but what if the battery suddenly hits 100% charge or the inverter gets too hot? The system has to cut that electric braking torque, and it has to do it instantly. If the driver is relying on that deceleration, that sudden loss of braking can lead to a loss of control. It's a very severe risk.
And what safety target does a hazard like that require?
It mandates ASIL-D for braking torque management. ASIL-D is the highest automotive safety integrity level there is. It's reserved for systems where a failure could be life-threatening. To achieve ASIL-D here, the truck needs seamless brake blending. The electronic braking system has to constantly monitor what the driver is asking for versus what's actually happening. If the electric torque drops, the regular air brakes have to compensate instantly and smoothly so the driver feels absolutely no change.
Okay, now for the highest risk scenario, the one that's specific to the mixer, unintended drum rotation. This is where safety becomes non-negotiable.
Hazard example 2. This is when a maintenance person, a chipper, is physically inside the drum cleaning out old, hardened concrete. If a software bug, a stray signal, anything, causes that powerful electric motor to start turning the drum, the result is always fatal. The HARAC classification is explicit. Severity is S3, fatal. Exposure is E3, a routine operation. And controllability is C3, impossible for the person inside to escape. That combination automatically mandates the highest rating, ASIL-D.
And an ASIL-D rating means software alone isn't good enough. The FSDS demands a redundant safety system, a dual interlock. How does that work?
It's a zero-trust system. First, you have the soft interlock. That's the software logic in the main vehicle controller. It confirms the maintenance hatch is open, and it digitally inhibits any torque command. But ASIL-D requires you to be safe even if the software fails. So you must have the hard interlock. This is a physical high-voltage interlock loop, an HVIL switch, right on the drum's inspection hatch. When you open that hatch, it physically breaks the power circuit to the motor's inverter. It makes it impossible for current to flow, no matter what the software is trying to do. It's a mechanical guarantee of safety.
Moving from safety to pure survival, this vehicle has to endure extreme heat, dirt, and daily power washing. Let's talk about thermal management.
The FSDS modeled the absolute worst-case scenario.
Yeah.
The summer full-load traffic jam. You've got temperatures over 45 Celsius, the truck is fully loaded, stuck in traffic demanding peak motor power to inch forward, and running the ePTO, all with zero airflow for cooling. If the system overheats and shuts down, it's a mission failure.
And the solution is these independent triple liquid cooling circuits. Why 3 separate ones?
The separation is critical because each component has a different happy place, temperature-wise, and you can't let heat from one contaminate the other, so you have a high temp loop around 90 degrees C just for the engine, a medium temp loop around 65 degrees C for the P2 motor and the power inverters, and then a low temp loop between 25 and 35 degrees C dedicated only to the battery pack.
Why is that low temp battery loop so critical, and why does it need active cooling with a chiller?
The battery's lifespan and performance absolutely depend on staying in that tight 25 to 35 degree window. The LFP battery chemistry is robust, but it's very sensitive to sustained heat. And the battery generates its own heat, especially when it's continuously discharging to run the ePTO while sitting still. So that low temp loop must be independent and must include a dedicated chiller, basically a refrigerant heat exchanger tied to the truck's AC system. This active cooling is non-negotiable to prevent thermal runaway and to get the full service life out of that very expensive battery.
Finally, we get to protecting it all from the environment. Standard IP67 water protection is clearly not going to cut it here.
Not even close. This truck gets blasted every single day with high-pressure, high-temperature water jets to get the cement off. Standard IP ratings fail instantly under that kind of assault. So the FSDS requires that all the upper components, the ePTO motor, its controller, the connectors, they all must be rated to IP69K.
And what does IP69K actually guarantee?
It's the highest protection level. It specifically certifies that a component can survive being steam cleaned with high-pressure jets. It's essential for surviving daily fleet cleaning. And beyond that, the control units have to have special breathable vents, like Gore-Tex membranes.
Why do you need a vent if the box is supposed to be sealed?
It's for pressure equalization. If a control box gets hot inside and then you suddenly blast it with cold water, you create a huge vacuum inside. That vacuum can suck moisture right past the seals. These vents let the pressure equalize, but they block water, and critically, they block the fine, conductive cement dust that would otherwise get inside and cause short circuits.
This FSDS really proves that modern heavy vehicle engineering isn't about brute force anymore. It's about strategic, detailed requirements decomposition. This P2 Hybrid Plus ePTO system, it's not a patch job. It's the calculated, optimal solution at the intersection of regulations, the duty cycle, and customer TCO.
That's exactly right. The FSDS confirms that the core value being delivered is the monetization of downtime. The key takeaways for any manufacturer looking at this are really fourfold. First, you get guaranteed long-term compliance with global emissions rules by maximizing those hybrid and idle reduction credits. Second, you deliver massive TCO relief by cutting idle waste. That results in a 25 to 30% overall fuel saving while also eliminating that long-term engine damage from wet stacking. Third, you actually expand the market for your customers. That sub 72 decibel silent mode turns noise from a liability into a competitive weapon, unlocking that 24/7 operational window. And fourth, it's confirmation that the 400-volt LFP P2 platform is the right tool for this job. It prioritizes industrial ruggedness and cost control over marginal benefits like charging speed, which this application just doesn't need.
So with all these goals and the architecture defined, the FSDS demands immediate action. What are the very next steps for the engineering team?
The directive is clear, and it's three-parter. First, they need to initiate RFQs for the highly specialized components like those IP69K rated motors. Second, they have to start the complex 1D thermal simulations to prove that triple cooling circuit can survive the worst-case heat scenarios. And third, they must immediately finalize and implement the ASLEOD safety logic for that maintenance interlock. That is a day one priority.
So what does all this mean for the heavy vehicle industry as a whole? This blueprint shows a shift from just designing trucks to designing mobile, energy-optimized work platforms. The ability to measure and monetize downtime, to turn what was once just costly, polluting idling into quiet, profitable electric operation. That is the fundamental competitive advantage defined here. It turns pure waste into sellable time. So the ultimate question for every heavy vehicle manufacturer right now has to be, if your biggest competitor can operate silently, efficiently, and profitably while their truck is just sitting there, can you really afford for your truck to just wait?